Welcome back. Today we're going to get into regression in some considerable detail. We're going to focus on least squares regression. We will take a look at other kinds of regression in future lessons, but today is all about some of the details associated with least squares regression. In fact, the plain ordinary type we've been looking at so far, which is called ordinary least squares. We're going to look at the details. We're also going to apply vector notation, and we're going to use the Einstein summation convention quite a bit. I would like to congratulate you all. You are part of my grand experiment to introduce the new notation to this discipline. All the formulae we're going to get will be exactly the same that you'll get elsewhere, but they'll be in our new notation. At least it's new for this discipline. I don't think it's too much extra complication. In fact, I think actually it helps out quite a bit. Only time will tell. Let's have some fun with it. So, we're going to talk about regression. Let's take a look at the basic linear regression model. That's where the data is equal to some intercept, plus some slope times time, plus some noise value. The noise might be measurement error so that the data is actually exactly equal to the straight line, but we have measurement noise. Or the data might include some random stochastic part so that the data itself, the signal, has randomness to it. In any case, our model is that the data is intercept plus slope times time plus a random part. This particular model uses two trial functions, at least that's what I call them. One of them is a function of time psi1 of t, which is the unit function. It takes the value 1 at all times. The other one is a function of time which is just the time function. Psi2 of t is equal to t. Now those two trial functions define two trial vectors by taking their values at the times of observation. First is the unit function, which defines the unit vector, psi sub j1, which is the unit vector subscript j. It's just the value 1 everywhere. Second is the time function, which defines the time vector, which is just the set of observation times. So our model is that a data value is equal to some parameter times our first trial vector, plus some other parameter times our second trial vector, plus some stochastic part. We can call it noise if you want, even if it's not necessarily noise. I'm going to write them as Greek letter subscripts instead of Latin letter subscripts. So it's the same equation. I just substituted alpha for j. There are two reasons that I do this. One is it helps us think of them as vectors rather than individual components, although we'll actually think of them and treat them as individual components at various times. Another is that we'll use the Einstein summation convention quite a bit. And we could think of it that way and use the Einstein summation convention, even if we used Latin alphabet subscripts. And we're not going to be too fussy about things. Notation is our servant, not our master. What if we had more than two trial functions, trial vectors? What if we weren't just doing linear regression so the model was a straight line, but the model was some other more complicated function? What if we had trial vectors psi sub alpha 1, psi sub alpha 2, etc., all the way up to psi sub alpha r, so there are r of them? Well, in that case, we would need our parameters. And our model would be that x sub alpha is beta 1 psi sub alpha 1, plus beta 2 psi sub alpha 2, plus beta 3 psi sub alpha 3, etc., up to beta sub r times psi sub alpha r, plus a random term. We can think of the beta values as forming a vector. But it's not an n-dimensional vector like x is, n being the number of data points. It's an r-dimensional vector, where r is the number of trial functions, trial vectors. So it resides in a different vector space. After all, it has a different dimension. I'm going to use uppercase Latin letters, capital letters, for that kind of vector subscript. It's to distinguish it from n-dimensional vectors that we're using for the data values. We're going to use the Einstein summation convention for uppercase Latin indexes as well as lowercase Greek. Then we can write the model in this way. We already know that x is equal to the sum of each parameter times its corresponding trial vector plus noise. I'm just going to write it like this. And the fact that the uppercase Latin letter A is repeated means we should sum over all possible values. By the way, that's the fact that it's repeated in a product. If it were repeated in a sum instead of a product, we wouldn't actually apply the Einstein summation convention. Or I should say, the Einstein summation convention wouldn't apply. Then I don't have to write the summation sign. It's implied by the repeated index A and the Einstein summation convention, which I think is pretty cool. The quantities psi sub alpha A, we can think of them, and we have so far, as a set of n-dimensional vectors, psi sub alpha 1, psi sub alpha 2, etc. up to psi sub alpha r. And there's one for each A value, so there are r of them. But another way to think of it is to think of it as a matrix. It's an n by r matrix. N data points are trial vectors. It's called the design matrix. Note that it's almost never a square matrix, because in almost all cases, the number of data points is not equal to the number of trial vectors. For a given set of parameters, the residuals are given by this equation. And notice that I have a sum over all possible values of A because it's a repeated index in a product, so the Einstein summation convention applies. The sum of the squares of the residuals is just this sum, but I can write that compactly using the Einstein summation convention like this. And because the lowercase Greek letter alpha is repeated, I sum all over all possible values of that index. Now I'm going to expand that sum of the squares of the residuals. What I'll get is just this times this. Notice that I used a different subscript letter in this term, I used A, than in this term, I used B. Why did I do that? Because I want the summations to come out right. This sum is independent from this sum. The index values in this sum do not have to match those in this sum. It should include all its cross products if you work it out algebraically. Because I want the summations to come out right, I used a different index letter to indicate that this sum is over all possible values of A, and this sum is over all possible values of B. They're different sums, so I use different index letters to apply the Einstein summation convention. Now, getting the summations right can sometimes be a little tricky until you get used to it. Once you do get used to it, I think it'll come naturally and easy to you. Do bear in mind that any repeated index which leads to a summation is really just a dummy index. It doesn't matter what it is, as long as it's the same on all the terms that have to have the same index value in a sum. Now, back to our derivation. We want to find the best parameters. We do that by minimizing the sum of squared residuals, and we do that by requiring that the partial derivative of the sum of squared residuals with respect to each and every parameter has to equal 0. And this leads to this equation, and I'm using the Einstein summation convention on both alpha and on B, so that here in this term, I'm summing over all possible data values and over all possible coefficients or parameters. Well, I can rewrite this equation just by bringing this term over to the right-hand side and dividing by 2. And I get the equation that defines the parameters. It looks like this. Now I'm going to define a matrix that I call the S matrix. The S matrix, the AB component of it, is the inner product of trial vector A and trial vector B. It's inner product because I repeated this subscript alpha, so I'm summing over all possible values. Now, because of that, I can rewrite this equation just by substituting that for that, and I get S matrix times parameter vector is equal to the inner product of the trial vector with the data values. I'll also point out that the S matrix, it's determined by the trial vectors, and which is determined by the trial functions and the times of observation. But it does not depend on the data values. There's no X anywhere in this equation that defines what the S matrix is. So I can determine the S matrix as long as I know what the trial functions are and when the observations are taken. That is to say, as long as I know what the trial vectors are, even if I don't actually know what the data values are. In fact, if I know what the trial functions are that I'm going to use, and I know the times at which I'm going to take data, I can determine the S matrix even before I've got any data, before I've done the experiment and taken any measurements. There are a few notes that are useful about the S matrix. One is that in this particular term here, the sum over B really makes this matrix multiplication. The Einstein summation convention says sum over all possible values of B, and that's just this type of sum which is the definition of matrix multiplication. Matrix times vector. Another thing to be aware of is that the S matrix is an R by R matrix. It is the inner product of trial vector A with trial vector B. There are R trial vectors, so we'll have an R by R square matrix. Also, it's a symmetric matrix. S sub AB is equal to S sub BA. That's because the inner product is a symmetric operation. The inner product of trial vector A with trial vector B is the same as the inner product of trial vector B with trial vector A. Another thing to be aware of is that the S matrix is positive definite. Now that's the case when all of the trial vectors are reasonably well behaved. Sometimes they're not, if you kind of make a poor choice of trial vectors. For instance, if I chose a trial vector which was 0 everywhere, then the only influence it can have on my model is nothing. In that case, my model would be ill-determined. And it would show up as the fact that, first of all, the solution we're going to get wouldn't really work out right. But it will also show up in the fact that the S matrix might not be positive definite. It might have zeros for non-zero vectors. But when the trial functions are chosen appropriately, the S matrix is a positive definite matrix. And because it's a symmetric matrix and it's positive definite, it has a matrix inverse, which we'll just call S inverse sub AB. Now we're ready to solve. We had the equation which defines them. It's right here. I'm going to take this matrix, this equation, multiply it by the inverse S matrix, and I'm going to get this equation. The parameters are equal to the inverse S matrix times the inner product of the trial vectors with the data value. Now, in the usual notation that you'll see in many courses, this would be written in this way: psi being the design matrix, x being the data values. You would take psi transpose times psi, compute its inverse, and multiply that by the transpose of the design matrix, and finally multiply that by the data vector. Well, these are actually the same equation. Psi transpose times psi in the old notation is the S matrix. Its inverse is the inverse S matrix. And psi transpose times x is psi sub alpha b times x sub alpha. The reason I have to transpose it is, notice here I'm summing over alpha, which is the first index component of the design matrix, and of course under the index component of the data values. In order to get this dimension to sum with the first one here, in old notation I would have to transpose this matrix. The only point here is that the old notation really gives you the exact same equations. It's just written in a way which I think is a little clumsier and harder to conceptualize. Others might disagree with me, but I'm trying to introduce this new notation. I hope it makes things clear for you, and I certainly like it. Now, this is exactly what we did with linear regression, except we now allow as many trial functions, trial vectors as we want. We arranged the trial vectors into a matrix, psi sub alpha A, which is called the design matrix, and which determines the S matrix. But the final result, that parameter values equal inverse S matrix times inner product of trial vectors with data values, is exactly the same as we had in linear regression. It's just that in linear regression, we had some simpler formula because there were only two trial vectors.